Hello everyone, I'm Li Xinliu from Tsinghua University. In recent years, satellite operators have been investing more and more into LEO constellations. However, these investments are not translating into proportional returns. In this talk, I will show you why this happens and how we can address this problem by rethinking what user terminals can do. LEO satellite networks are booming at an unprecedented speed. The number of operational LEO satellites has grown rapidly in the past few years. Starlink alone plans to deploy 42,000 satellites, and Amazon LEO and other constellations are also scaling aggressively. From a capacity perspective, this looks extremely promising. More bandwidth, global coverage, and low latency. So at first glance, it seems that LEO networks grow better and better. This rapid growth comes with massive investment. Satellite operators are spending tens of billions of dollars to deploy these constellations. With such massive investment, one would naturally expect massive returns. But that's not what we observe in practice. Here is a surprising observation. Despite the massive constellation size, over 90% of Starlink satellites operate at less than 20% capacity utilization. This means most satellites are idle most of the time. So the core problem for operators is not a lack of satellites. It is why this capacity cannot be efficiently used. Interestingly, the bottleneck is not in space, but on the ground. Today's LEO networks still heavily rely on ground stations to land traffic. Satellites without access to ground stations are forced to stay idle. Even if satellites can forward traffic through ISLs, eventually data must land on the ground. As a result, GSL capacity becomes the bottleneck. Satellites above oceans or remote regions remain idle most of the time. However, in practice, space is over-provisioned, while ground access is scarce. A natural idea is to add more ground stations. More ground stations can mitigate GSL bottleneck and utilize idle satellite. Unfortunately, this doesn't scale well. First, ground stations are limited to the land, less than 30% of the Earth's surface. Second, they are expensive, costing up to $50 million per site. And third, the return on investment is poor. A 3.5 times increase in investment only brings 0.73 times utilization improvement. So simply building more ground stations is costly, slow, and inefficient. Another approach is to better utilize existing ground stations. As we can see, traffic load is unevenly distributed across ground stations. Some are overloaded, while others are underutilized. Therefore, pre-work proposes using ISLs to balance load across ground stations. This helps, but only a little. GSL bottlenecks still exist. The overall utilization improvement is little, and ISLs are operationally constrained in today's LEO networks, so this approach alone is not enough. A more radical idea is to redesign the constellation. For example, some work explores non-uniform constellations and multi-operator designs, aiming to reduce the number of satellites and reduce capacity waste. However, clean-state designs are hard to retrofit into operational LEO networks, where massive idle capacity already exists. So we asked a different question. Can we unlock idle capacity without building new ground stations or launching new satellites? Our answer is CrowdLink. The key idea is to reuse user terminals as ubiquitous side links. This idea is based on three key observations. First, user terminals are already everywhere, and they already connect to satellites. Second, modern UTs have Ethernet interface to local networks and multiple beams to connect to different satellites. Third, UTs have idle bandwidth most of the time. So instead of treating UTs as passive endpoints, we repose them as relays and gateways, creating alternative landing paths and alleviating JSL bottlenecks. Therefore, idle satellite capacity can be utilized. This idea sounds simple, right? But to make it work in practice, CrowdLink must answer three fundamental questions. First, how to make it work in today's operational layer networks. And second, how to make it work well under extreme layer dynamics. And third, how to make it work well continuously with more terminals. Let's look at the first question, how to make it work. To answer this, let's briefly look at how today's layer networks work. Operational layer networks, such as Starlink, rely on a centralized controller for connection scheduling and gateway allocation. When a UT pops up, it first registers with the controller through the control path. The controller manages beam scheduling, gateway alignment, and routing. Once configured, the data path is established. This existing control framework gives us a natural place to integrate CrowdLink. Now let's see how CrowdLink fits into this framework. On the UT side, modern UTs are no longer dumbbell clients. They have Ethernet interface for local forwarding and two beams to connect to different satellites. This makes relay and gateway functionality technically feasible. CrowdLink only requires a software or firmware upgrade. On the control side, CrowdLink can build directly on the existing control functions. We extend it to support relay beam scheduling, UT gateway assignment, and inter-UT relaying. Finally, the controller establishes an end-to-end encrypted tunnel between UT and the POP, just like today's layer networks. And all forwarding is transparent to satellites, requiring no modification to satellites or ground stations. The second question is how to make it work well. In layer networks, satellites move extremely fast, causing frequent link and topology changes. If UT-based relaying is tightly coupled to these dynamics, it simply won't scale. Our key insight is very simple. Satellites move, but UTs are stationary. So we stabilize inter-UT logical links using coordinate beam scheduling. Based on this insight, we construct a gateway UT rooted stable tree. This process has three steps. First, a joining UT searches for candidate relay or gateway UTs already in a tree. Second, it selects the best candidate as its parent. Third, it attaches to this tree by duplicating beam schedules of its parent. This creates a UT-level stable topology that can mask satellite dynamics. Once the tree is built, relaying paths can be computed efficiently by simply reversing the tree. Because the UT-level tree is relatively stable, CrowdLink can scale to a large number of UTs, even under extreme satellite dynamics. CrowdLink also supports multipath relaying. If UT in different trees share the same beam schedule, the controller can establish logical links between them, forming a stable UT-level graph. Through this graph, a UT can be assigned multiple gateway UTs, enabling higher aggregate bandwidth and better satellite utilization. The third question is how to make CrowdLink work well continuously. User terminals are owned by users, not by the operator. Their participation cannot be taken for granted. To make CrowdLink sustainable, we propose incentivizing UTs with rewards. UTs that request additional paths pay for the service, while relay and gateway UTs receive rewards proportional to the traffic they forward. The remaining question is how to incentivize participation efficiently. Because user demand and UT distribution are highly uneven, we propose a geographic demand-aware dynamic pricing mechanism. We estimate load at both UT and region level, dynamically adjust per unit reward price, and give UTs with high topological importance additional bonus. This exactly encourages UT participation where capacity is scarce. To evaluate CrowdLink's feasibility, we built a real prototype on Starlink dish across 3 countries. Since Starlink is a closed, non-public system, we adopt a non-intrusive design. All CrowdLink functions run on hosts behind the dish, and traffic forwarding is completely transparent to the operational satellite network. Let's look at the evaluation results. First, the overall benefits. CrowdLink improves per UT throughput by about 3 times on average, and more importantly, it doubles total capacity utilization. This means CrowdLink converts idle satellite capacity into actual service capacity, directly improving operators' return on investment. Here are macro benchmarks from our prototype. The results show that CrowdLink improves end-to-end throughput for both UDP and TCP traffic. This confirms CrowdLink's practical feasibility. Finally, we examine scalability. CrowdLink significantly stabilizes relaying paths and reduces signaling overhead as the number of UTs increase. This shows that our UT-level topology abstraction effectively hides satellite mobility and scales with the number of participating UTs. To conclude, our work shows that more satellites do not necessarily mean better utilization. The real bottleneck lies at ground stations. Instead of scaling by building more infrastructure, CrowdLink lets the network self-scale from its users. Inspired by P2P, CrowdLink repurposes user terminals as relays and gateways, unlocking idle satellite capacity without adding new infrastructure. In the long run, CrowdLink represents a user-centric paradigm for scalable and sustainable LEO networks, and we believe this paradigm can go even further. Beyond improving utilization, it opens up a new design space where user terminals become active building blocks of the network, enabling more flexible capacity sharing and better resilience under constrained infrastructure. Thanks for your listening.